Okay, chapter 10 is about the panel data. So how about the panel data? You can see a notation with the I and T. I's mean the observation. Okay, so and T is time. So in your maybe I open this textbook. Okay, so I open this textbook data. So here is okay, totality. You can see here we have some in the column 1 is about state, column 2 is year, and you have some variables in this data set, so you can see this data. And for the AL state, you can see this observation from the 1982 to 1988. So they have 7 years data for each state. And for the AZ state, you can see from the 1982 to 1987, in 1988. And AR is the same. Okay, so you can see all the data. Each state, they have about 7 years data. Okay, so if the data set without the NA, so omissive observation, we define is a balanced panel. If the data set has the missing, we say about this is a unbalanced panel. And so I check this data set with this comment. They have the 2 missing values, so it is not balanced panel. It is unbalanced panel for this data set. Okay, so and then we can see these 2 scatter plot. In 1982, in our background knowledge, we can see these 2 variables should have a negative relation. But in 1982, you can see this scatter plot, they have a positive relation. It's not make sense, so we should make some adjustment for this data set. We see another year again. In 1988, you can see these 2 variables also have a positive relation. So we should think about some adjustment for this specific data set. This is a panel data, so we should use some specific method to deal with this problem. Okay, so method 1, is mean another textbook is say about first difference. Maybe in the time series chapter, in our textbook is chapter 15, but in our semester we don't discuss this topic. Yes, maybe in chapter 15, Stock and Watson. And in other textbook is say this method is about first difference. What is the first difference? You can see about at first we have a simple example. We have a 2-year data. Maybe in our example it's about 1982 and 1988. So first is about why 1982, 1988. Data 0, data 1. So I use the notation upper one. I use only requests in our model. In the second year, we also use one requesters in our model. And first difference mean we make difference for these two equations. So we can see here, in the right hand side, we have a y1 minus y2. In the right hand side, you can see here is about something, maybe new intercept plus the new slope times the new x. New x is about x1 minus x upper 1 minus x upper 2. So we have a new dependent variable and new independent variable. So we use these two terms to run the regression. Okay, so I do this by the R. At first, I make a difference variable for these two common. I run a regression. You can see this result. They have a negative relation between these two variables. It makes sense. Okay, so we can see the scatter plot here. These two terms have a difference. They have a negative relationship. This result makes sense. Okay, so it's a method 1. Okay, and method 2 is about a fixed effect. Okay, so how about a physics effect? Okay, so at first we discuss the state physics effect. So we only focus on the condition on x, not for time. So we only focus on the I, no t. So we only focus on I. So In the original model, you can see here, we have an intercept and a regressor. And Z is unobserved variables. It's not changed for any time. So it is about one turn in the physics effect in the alpha. So alpha is about beta naught plus beta 2 times Ci. So you can see this is original form for the state physics effect. And if you have a n state, so I is equal to 1, 2, to n. You have an n state. You can transform this original form to this one. You can use a n dummy variable. So if a state 1, you can use a d1 dummy variable. In a state 2, you can use a d2 dummy variable. And if a state n, you can use a dn dummy variable. Okay, so maybe I have some typo here. Here's a n minus 1. Okay, so because we only choose all dummy variable without the intercept, or n minus 1 dummy variable with the intercept, we have a two choice. Okay, so this is a construction for the state physics effect. And now we change to focus on the time physics effect. We focus on the t. So t is about equal to from 1 to capital T. And lambda is about time physics effect. So we can transform to original form. We have a intercept and a unobserved variable for the time physics effect. And we can use a all dummy variable again. We have a t period in our data. So we can use a b1 in a t equal to 1 for capital T when t equal to capital T. So we can use all t dummy variable here. So I should change here capital T minus 1. Okay, so here I ignore the t equal to 1. So I don't change here. So here is about T1 y. So here is not, we have no typo here. We should focus on the D1. I ignore the term is B1 and D1. Okay, so we can also combine these two physics effects in the one model. So this is about maybe in your homework 5, you should make some proof to find a relation between these, maybe alpha, lambda with x and z. Okay, so we can first all turn in the one model. Here is about alpha is about state physics effect. Lambda is about time physics effect. For the D2 to Dn turn is for alpha, and B2 to B capital T is for lambda. Okay, so here's one important sentence from your textbook. So I copy to here. For this combination model, include a state physics effect and time physics effect. Okay, so it don't have an omitted variable bias because we only evaluate this term in our physics effect here. So we don't have an omitted variable bias. Okay, so because we assume these omitted variables have no change for each period, we can use you can imagine to the first difference. When you do the difference, you can minus don't have each term in the difference model. So physics effect is the same, but you use a different construction to make the same thing. Okay, so I also do it by R. In R, you can use the dummy variable directly for Lm common. So in Lm common, you should use a factor for the state variable because you should create a dummy. And in our model, we also use the heteroscedasticity or robust standard error. So we should, in Lm common, we use a homoscedasticity standard error. So you cannot use the constant variance assumption. We usually use the robust standard error in the panel data. So we should calculate the robust standard error by VCOV. Maybe you can use a LN robust because this stargazer, I cannot use the LN robust to this output common, so I should use the LN. But in your R, you can use the LN robust common directly. So here I use the LN and BCOV to find the covariance matrix, and I choose a diagonal term to make a square and make a square root. So I find their variance and find a standard error, robust standard error. And in R, PLM is about panel data linear model. So P is mean panel data. And in our example, we use the I should see here. Y on the beer text, maybe I should see how about Y. Fatality rate. So fatality rate on the beer text. So we should use these two variables, y on x, y delta x. And you should define your user data. And you should talk to R. What is your time and state? So here is I, state. Year is a T, about T, year. Okay, so you should say talk to R. What about your I and T? And model, you can choose some different choice. It's a within choice is about physics effect. So within is about physics effect. And we use the individual effect tool here. Okay, so if you want to use both, maybe two-way, it's about time. Okay, so here is about only state. State physics effect. And I find the robust error again. In here, we consider the state effect and the time effect by the dummy variable. State and time effect, time physics effect. Okay, and here is I use the package in R, POM. I also use a panel data model, linear model. I use the I and T again. Use a within because I want to use a physics effect model. And two-way is about state and time physics effect in our model. Okay, so how about we can see the result? Okay, at first we focus the first two column here. For the column 1, we use the state physics effect by the dummy. Because I don't use the minus the mean for the variables. So in our model we have a constant term. If you minus maybe y minus y bar on the x minus x bar. If you use this term, we don't have the maybe times the t or n capital T. Maybe like this. So if you run this model, you don't have the constant term. But in our comment, I only use the dummy variable. Don't change for the minus layer means. Okay, so I have the constant term here. So we can see this slope for beer text is the same for the panel linear state panel physics effect common in R. Okay, so we can see they are the same. But in standard error, there are some difference because we use the constant in a dummy variable model. Okay, so how about the state and time physics effect? You can also see the constant term for the dummy variable model. And if you use the PLM, it's about plano linear model. We don't have a constant term, but the slope for the vertex, they are the same. But center errors, they are different. Okay. And so in these two models, we cannot directly compare this R square because in our model setting, they are the same. You can see here, in our model setting, they are the same. We evaluate this term or this term or this term. They are the same. But in the programming software, the software cannot know they are the same. So maybe you see the result, you are confused for this result. But in the model setting, they are the same. So I cannot directly compare these two models R squared. And these two models is the same thing. We cannot directly compare these two R squared because in our model setting, they are the same. You can see here, we run this one and this one, this one and this one. In our model setting, they are the same. But in the programming result, there are some different for some statistic for the model, not for the slope. Okay, so how about and now I discussed the classwork last week. At first, it's about exercise 10.2. This question is about, okay, so consider the binary variable physics effect model. Okay, so in this model, you can see here, you use the O state from the state 1 to state n. You cannot use O state in the model if you use the intercept. So you only have two choices. Without beta 0, use all state dummy, or with the intercept, use n-1 state dummy. You only have two choices. So here, you use the intercept and all state dummy. So you have a dummy variable trap problem here. So in the question 1, it says about if n equal to 3, please show the perfect linear collinearity for this problem. So you can see here, d1 plus d2 and plus d3 is equal to 1. Because if you have a 1 observation, it have a 1 condition, 1 state from the 1 to n. So you should have the 1 state. Maybe it's 1, maybe it's 2, maybe it's n, or n-1. I don't know. But you should have a 1 state in your observation. So your result is 1. How about for general form? d1 plus d2 plus to dn is equal to 1. So I finished this question. Or maybe I have a part C. What problem about if we run this all dummy variables with the intercept? In R, we will ignore the last term, state dummies. D and I. So we cannot have the slope for the dn in R. If you run the all dummy variables, run all state dummy variables in the intercept in your model, you can do it by yourself. Because maybe I can show after this question. And how about the next exercise 10.7? Okay, so the researchers so he want to discuss the one occurrence of the disasters maybe lead to increase the construction industries, because we don't, after the disaster, the factory is broken. So he want to find the data for the earthquakes and industry. Okay, so here you use a indicator variable. Maybe you can see as a dummy variable or categorical variable. They are the same in the model setting. If this variable equal to 1, it's about earthquake took place in that place for the last 5 years. Okay. So you should know some information in this question. Part A. Should the researchers include this physics effect to control the location for the labor market? Okay, so maybe you should define some. Okay, solution 1 is about you can do it, correct some information to do this by the programming. And you can find some problem when you run the code. Okay, so the answer is no, because this physics effect will be perfect linearity for the earthquake indicator, maybe disaster indicator or in disaster dummy variables. So the exercise 10.7, he do the same thing for the exercise 10.2. You can see here about here. If you have you can see this is about physics effect for the earthquake or disaster in other natural disasters. So here you can see here, if you use the O indicator, you can have a dummy variable trap or perfect collinearity in your model, so you cannot use this model. Maybe this question is not clear, so I don't think this question is not well. And part 3 is about what can the researchers to control the location effect. So this part focus on the location effect. So maybe you should find some location characteristic to control these variables. Okay, so in our problem, he say about he want to find this causality between this disaster and industry. So maybe he impact on the labor market. So how about it? So maybe we can find some information to the labor market. So maybe employment or unemployment to do the phase effect. Okay, so if you cannot find this information for the labor market, maybe you can focus on another related variable for the labor market or the industries. And exercise 10.10. This question is about, okay, so researchers, annual earning, age, gender, schooling, union status, occupation, employment. Okay, so he say he collect the panel data. He want to regress the annual earning on, so it is a y, and its determinant variables. Use the phase effect to control for an individual's specific time invariant characteristic. So this is something you should focus on these standards. There are some problem here. What estimation problem is he like to? It is a question mark. If he use this strategy, he has some problem. So what is he problem here? Because how about your age? Different type has different age. Okay, so it's a time invariant. How about gender? Maybe at the first t equal to 1. Maybe he is a male. Maybe he do something, so t equal to 10 is a woman. But in our society, we still don't have a data for if he or she, it is data on when t equal to 20. It changed the gender again. It's not make sense. So is some problem here. How about schooling? After when you graduate from maybe college, how many years you have in the elementary school? 6 years. 4 year in a junior high school. 4 year in a 3 year in a senior high school. 4 year in a college. So maybe you have a result 16 year. So if you college level graduation is about education is about college, you have the school is 16 year. We don't have a change for any time. So you also make some not good variable here. So gender is not good, schooling is not good, and union status maybe is not good because if all the data when a t equal to 1 in a place 1, when t equal to 2 is in a place 2, if all the data is have the situation here, you can use this to evaluate the time physics, to evaluate the control the physics effect, but it's not make sense in your data, so it's not good here again. How about occupation? You can change the occupation every year, so it's not make sense. So all the variable in this is his data. It's not good for the physics effect model. So this question it has many problems in his model. So okay, so I can see the okay. So maybe I change to another topic. It's for the homework 5 coding.